this introduction. So I will talk essentially, carry on following up from the plenary session on Monday, go into a bit more detail about the construction of a predictive neuron model using large-scale data assimilation. So this work was done in collaboration with Andrea Barbanel at UCSD and colleagues also at Virginia University and the University of Chicago. I'll also talk about the construction of a hardware model, so in essentially a central pattern generator device that we use in heart failure therapy. And this is a collaboration with electrophysiologist Julian Patton and his group at the University of Bristol, cardiologist at the NHS hospital in Bristol, as well as the people from the Bioengineering Institute at the University of Auckland. So in terms of building neural model with data assimilation, essentially we'll be building a multi-channel conductance model using assimilation of electrophysiological data. And the models will be validated through a prediction from a wide range of injection protocols. And we see that data assimilation needs to be boosted by Bayesian inference to reach the graal, which is to obtain a single-valued model. And I'll talk about a few further applications to neural networks, so new therapy for cardiorespiratory diseases, and time-allowing control of switching between cardiac attractors. And our data assimilation can be useful for engineering the basins of attraction. So just a word about Bath. The name comes from the existence of Roman baths in town, and we are located in the southwest of England. So to start, what a neuron is essentially a current-driven nonlinear oscillator. So if you inject current through the neuron, then as you increase the amplitude of the current, the membrane voltage will remain quiet, and above a certain current threshold, the neuron will start, the voltage across the membrane will start oscillating. If you keep on increasing the current, the oscillation frequency will increase. So this kind of behavior was first explained by Hodgkin and Huxley, and then essentially they devised a model that explained this behavior by modeling the electrically equivalent circuit of the neuron membrane. So this includes the membrane capacitance, and they were very careful in modeling the conductances of potassium and sodium ions. So essentially, these are these terms. So this conductance is proportional to the maximum conductance, and then also to these numbers M, H, and N, which describe the probability for each of these ion channels, ion gates, to be open. So essentially, the rate at which the voltage across the membrane changes is proportional to the sum of the currents through the membrane plus the current which you inject with your current clamp externally. So this is the first equation of the Hodgkin-Huxley model. There are three more free-rate equations that describe the fact that the gates do not open instantly. So why do we have three equations? It's very easy to see. So it's basically we got two types of ion channels, sodium channels and potassium channel. The potassium channel has got a single gate. The sodium channel has got two gates. Therefore, you need three probabilities to describe the state of the free gate. So these gates do not open instantly, so you need a rate equation and an associated time constant to describe the rate at which these ion channels open and close. So the time constant depends on the voltage, it depends on three parameters. And you also have the nonlinearity of the response, ion channel response, is given by a sigmoid curve, essentially, whereby the probability increase as a function of gate voltage as the membrane increases. And this function here is characterized by the threshold at which this opens, and also the transition, the width of the transition. So essentially, this is just to introduce to you the fact that in order, this ion channel is characterized by 1, 2, 3, 4, 5 model parameters. Now, this is only for the potassium channel. For the sodium channel, you have 2 gates. Therefore, you got 5 plus 5, 10 model parameters. So unfortunately, life is quite complicated, and there are a wide range of ion channels. I've listed here a range of potassium channels, and each one is a protein which is coded by a gene, and each individual channels have got specific threshold voltage and kinetic. So in principle, if you are able to extract the values of this voltage and kinetic, you are in principle able to know which ion channel is active in the neuron. And this is one of the purposes of the data assimilation, to be able to sequence the ion channels in the neuron from electrophysiological measurement. So the same for, you've seen that there are many potassium channels. There are also quite a lot of sodium channels. So basically, you understand that the Hodgkin-Oscillator model is not sufficient anymore. So you need to add many more current, up to 8 current, to generate a model that will describe the generic behavior of more complex neuron, for which you find in birds or mammals. So basically, you got this range of current. Each one is proportional to maximum conductance, and also to the probability M and H for the activation gate, and H for the inactivation gate. So this is our model. So the voltage, the rate of change of the voltage is proportional. I mean, it's proportional to the sum of these ion currents. So the model is just the same, but slightly more complicated. Now we've got 12 state variable, which is the voltage, and each of the probabilities. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 state variable. You got 71 parameters, like voltage threshold, like conductances, time constant, and you got 12 coupled nonlinear differential equation. So these are the equations you have in the assimilation code. So how do we implement this optimization? So this the fundamental of the optimization rests on Taken's embedding theorem, which says that all the information which is required to constrain the model is contained in the observation of one state variable. For us, this state variable is the voltage across the membrane over a finite window of duration t. So we go to electrophysiologists, ask them to perform current clamp measurement, where they inject a current protocol, so a current at time interval T1, T2, T3, Tm, and they record the voltage induced across the membrane. Then you define a cost function which you want to minimize. So this cost function measures the distance between the observed voltage and the model voltage, the variable of the model y1. And this cost function depends on the parameters of the model and also the initial condition of the model. So the purpose of the game, obviously, is to get this, to minimize this cost function. And there is an additional regularization term, which is essentially to facilitate conversions. So there are constraints, two types of constraints, equality constraints and inequality constraints. So equality constraints derive from the 12 differential equations, which are linearized at each point of the discretized time window. So you got typically the time window, the number of mesh points here is 100,000. So multiplied by 12 differential equations. So you got 1.2 million constraints in the model. And you also have inequality constraints, which are the search interval you specify for these parameters. So the lower boundary and the higher boundary. And essentially these constraints are the only human subjective input in the assimilation procedure. Then you build the Lagrangian, including the cost, the constraint, you include the inequality constraint as a log barrier. And so you construct a so-called Cauchy-Tucker system of sparse linear equation. And then you iteratively solve this system using the Newton's method. And on each iteration, you reduce the height of the log barrier until convergence is achieved. So when the procedure has converged, you obtain a parameter vector, which contains the 71 components are the parameter solution you are looking, and the regularization function hopefully should be equal to 0. So this is a typical list of the 71 parameters you're trying to extract. The range of integration you see here. So the first parameter will be the capacitance of the membrane voltage. If you are looking, for instance, for the voltage at which the sodium transient sodium channel open, you look for this the range between -45 and -15 millielectron volt, and the output will be, for instance, for one neuron -34 millivolts. So this is the list of the vector P that you get for each neuron, or if it's 71 components. So you can assimilate data and then to construct completed neural model, and after use this model for making predictions. So I'll go through that briefly. So in this diagram, what you see, the black line is the experimental voltage. This is behind the green line. So this is the voltage which is measured on the neuron when the neuron is stimulated by this current protocol here. And then you assimilate this data over this the window, the time window here. And when assimilation has converged, the best fit of, if you like, when the model is synchronized to the data, the variable y1 is described by the green curve. Then the curve that gives you this, the green curve will give you the parameter solution. You input this parameter solution in the model to construct the completed model, and then you can integrate this completed model with any arbitrary current protocol. You do that using, for instance, adaptive step size Honeycutter method. We use a fifth order method, and then you integrate use a model to integrate this current profile, and this is the predicted voltage, which you can compare with the experimental data. So you can see it fits quite well. Here is another example on a different neuron. Again, you got the assimilation time window is runs from 190 milliseconds to 1090 milliseconds. So you assimilate the data in this range, and you can integrate forward from that time to make your prediction. Again, you can see that you got a fairly good agreement. I quite like this prediction. No, these are real neurons. The black line, which is behind the green line, is a real neuron. I mean, these are the data which are measured. So these are these data you assimilate. You assimilate this data here, and then the green line, which is right on top of the black line, is the result of the assimilation. Okay. So basically, I was saying I like this prediction here because you can see that in principle, if you look at the sequence of current, the sequence of current pulse and this one, they are very similar. Here, the neuron fire regularly. Here, the neuron misses the black line. It misses three spikes. But nevertheless, you can see that the prediction allows you to identify the stochastic variability in the neuron. So I don't like to say that, if electrophysiologists don't like to say that, but the model is actually more accurate than the real neuron. Okay, so that's, I've said it, now you forget it. And then you can play, challenge yourself. So you can validate the models that you predict, that you construct by. So for instance, the model of neuron 1 and neuron 2. You can integrate any arbitrary current profiles And then you can generate the prediction, which are the red curve, which are on top of the experimental, which is the black curve. You can see the difference in places, for instance, here, where it misses, the model misses a spiking. But generally, you have a very good agreement between prediction and experiment, and this is the same for neuron too. So generally it works well. It doesn't work well for obvious reasons sometimes, here, where you can see that the model doesn't replicate the data, and this is simply because the rate at which the injected current is much higher than the cutoff frequency of the spectrum of the protocol that you use to do the assimilation. So necessarily there's some information which is missing in the model. So what we have done so far, we have predicted the state variable that you can measure, which is the membrane voltage, but you can also predict the response of the state of the ionic gates, which you cannot measure. So you can see the value of this model is that it allows you to make prediction about parameters which are not accessible to the experiment. At this present time, maybe in 10 years or 20 years, there will be a method for measuring the state of the gates, but not now. So when we try to build model by assimilating real data as opposed to model data, you run into a number of additional difficulty, which comes from the fact that you don't know the exact model. There is noise in the experiment. There is some assimilation window will be better at constraining the parameters than other assimilation windows. And there is stochastic variability in the neural output. So this induces uncertainty in the parameter field. So basically, we pack all this uncertainty, or this as a noise component, and try to assess what will be the effect of this noise component on the difficulty of reaching the minimum, the parameter state. So basically, if you look at the cost function, so you separate the data as a useful signal and the noise signal. So this is what I've split here. The data is a useful signal for the noise signal. You expand this, so you regroup the square term, which is the useful minus the data, and then you have an additional cross square that comes from the square of the noise, and you got an additional cross term, Vn times the product. So this additional cross term cancels because it's proportional to the noise average, which is 0. So what we are left here is the sum of the square on the noise voltage. Essentially, this recalls the variance of the noise, which is you can use the result of the Johnson-Nyquist theorem to recall that this is proportional to the temperature multiplied by Boltzmann constant multiplied by the resistance of the neuron multiplied by the bandwidth of the system. So if you can replace this sum in there, then you find that your cost function is equal to a cost function that now depends on the useful signal. So we call that the free energy. And then you've got an additional term which is proportional to T. And the coefficient of proportionality, this is the entropy of the noise signal. So it's quite nice because you fall back on all the equation in thermodynamics that the total energy of the system, the cost function, the free energy, you can minimize this free energy using a deterministic parameter search using data assimilation. And then you got a non-deterministic energy component, which is related to noise, that can only be used by statistical inference. So basically, there is the morality is that there will be a minimum data misfit delta C, which is proportional to ST. So you can never get to minimize the total energy by simply data assimilation. So we have seen that noise behaves like a residual temperature that prevents reaching the global minimum through direct parameter search. So what does this delta C surface looks like in parameter space? So you can expand the cost function relative to P near, in the vicinity of the global minimum. So this is the cost function here, and the Taylor expansion will give you these terms. So essentially, geometrically speaking, this is the surface of an ellipsoid in 71 dimensions. On my diagram, this is this plot. So when you do parameter search, then you data assimilation, you follow a path down the slope down to this ellipsoid, but you can never reach the global minimum because of this kT residual energy or temperature. So basically, in order to, I think we have done some characterization of this ellipsoid. I don't really have time to discuss about it. You can see in the publication. But what we're trying to find is what is the global minimum of the function. So basically, we have been running a number of simulations whereby we reach the ellipsoid from many different angles, if you like, by assimilating different segments of data. And what we do, we take the maximum likelihood estimate to approach the global minimum. And then if you do that, you find something which is very nice. You can see that the parameters, and in this specific case, the expectation value of the threshold for two different neurons of the high vocal center, they just line up with each other. So basically, that's first indication that you're probably close to the global minimum. So you got excellent agreement between the threshold voltage extracted from the 2 HVC neuron, and you obtain physically meaningful estimation. So this is not only the voltage threshold, but you've got many other parameters. So for instance, if you compare the activation curve for the equivalent ion channels for the neuron 1 and neuron 2, you can see they look very much similar. And then these are for the sodium channel, potassium channel. You can see that that's quite nice. So basically, the morality of the story, the take-home message is that if you want to construct a unique neuron model, you need to combine data assimilation with Bayesian inference to achieve single-value biologically plausible models. Okay, so the method is automatic, requires minimum biological intuition, and it's quite nice because it's sufficiently accurate to evidence trial-to-trial fluctuation in neuron behavior. So I think I've got a couple of more minutes. I would like to talk about the building of a hardware model and how data assimilation can be used for improving the models that we do. So basically, we are especially interested in heart failure. So what I'm showing you here is MRI scan of a healthy heart here, and a heart which is heart failure. So heart failure is a pretty serious condition, and which doesn't have a therapy at the moment. And typically 20 to 40% of people who are admitted to hospital with heart failure, they die within a year. So that makes there is a need, urgent need to find a solution. So a hint towards a solution is that the loss of heart rate variability is a prognosis of heart failure. One example of heart rate variability is synchronization between respiration and heart rate. So in a healthy individual, there are neural networks in the medulla, at the base of the brain here, which integrates physiological feedback, like arterial gas pressure, O2 and CO2, information from a stretch sensor from the lungs, and also from blood pressure from carotid and aortic baroreceptors. And this information is fed into central pattern generators, these networks. So essentially, the activity of this network branches around here, and these stimulate the heart rate, slow down the heart rate through this pathway or accelerate the heart rate through this other pathway. This is a sympathetic system and the vagus nerve system. So basically, this network here, especially important, is slowing down the heart rate at specific point within the respiratory cycle. So what data assimilation, what we are doing at the moment, we use data assimilation to try to infer the network connectivity that restores the accurate adaptation of the heart to these physiological feedback. So in the neuron model which I was showing at the beginning, we had one input and a single output, single voltage. Here the system is a little bit more complicated. The math is the same. So you have 4 inputs and 2 or 3 outputs. So I think I am more or less done. So I would like to show maybe some data that we got. So we looked at this closed loop whereby you have lung inflation stimulate the CPG and then feedbacks into the heart. And so this is this feedback loop here. So I'll go quickly. So we use some hardware model. So basically it's a 2-neuron network here to stimulate the vagus nerve. It's a 3-neuron network like in the above diagram to stimulate the sonoratural node. And you can see we can control the heart rate in phase with respiration. You can control the amplitude, also control the phase. And then if you do that, so this is some result of experiment in sheep, you can see that if you induce, so the heart rate is changed in phase with the respiration here. This is when the sheep breathes in. So this is the expiratory phase. So without modulation, the cardiac output is quite low. If you restore modulation, you increase the cardiac output, which is a product of the blood pressure multiplied by the ejection volume by 19%, eventually lead to remodeling of heart rate. So this is potentially useful as a therapy for heart failure, and data assimilation can make a big difference for that. So I think I'm done with time. So the data assimilation can also be used for engineering the attractors in chaotic neural network. So basically, I just conclude and thank the people who have been involved in this work and sponsors, and thank you very much for your attention.